classes, which is like a weird number. I say a weird number. So like here's us. Here's us today. The 24th of October. Then we have 1 week till the end of October. Then 2, 3, 4, 5. And that's it. And then after that, it's finals. So we're nearing the end, y'all. Withdrawal deadline, I think. What day is it? November 1st. All right, so this is true of any of your classes, my class, any other classes, if you're concerned about your ability to pass it or anything of that nature. November 1st, your deadline. It would have been great if we'd been able to have test 2 the day before that, and then I get all your multiple choice stuff graded. But yeah, obviously that's not going to happen because your test isn't until the 12th. It's going to be fine though. Hopefully, you all have started doing the energy stuff, considering one of the quizzes was due yesterday. But hopefully you've all started doing the energy and realized energy is really like straightforward. Whether or not you decide it's simple, it's at least straightforward. It's energy initial plus work equals energy final, work equals integral of force and distance. All right, so momentum. We might, and keyword might, there is a chance that we might finish this today. There's a chance. I'm not going to try to rush it. This is me not trying to squish it in here. That's not like, the goal is not like, man, try to get through stuff as quick as possible. But momentum is fairly straightforward. So like, okay, we did the forces stuff. To remind you all, I told you what momentum is. Where's it at? Momentum is m times v. And remember I told you all it's a vector. That's going to be the key phrase today, that it's a vector. That's one of the key phrases. And we were able to do a derivation, and we were able to derive something called impulse, which basically just said, hey, if you find your change in momentum, that equals an average force over some time. And we did some problems with that, and it was a great time. We had so much fun. And then the last thing I left you all with was the following, and this is what we're going to be doing basically all today. If you add up all your momentums in the beginning, they equal all your momentums at the end. The only caveat to this, as long as there's like no air resistance or friction taking away stuff. That's kind of the only, as long as there's no non-conservative forces, because this is fairly easy. So like, let me just give you all an example to show why it's obvious that this does not work if friction is happening. I push a box with a velocity of 3 meters per second. So that's my initial. And then there's friction. And so friction eventually makes it come to a stop. Look, if we just do the math, the momentum in the beginning is a number. The momentum at the end is 0. Obviously, that doesn't work. If mass is 1 kilogram, the momentum in this case is 3 kg m per s. What's the momentum if you're not moving? 0. Okay, so hopefully you all can obviously see if friction is present, it doesn't work. Like clearly, here's an example, it doesn't work because the environment affects things. But if there's no friction or air resistance, this always works. And you may feel like that's a strong limiting factor, but it's not, because often air resistance we can kind of ignore. It's usually not that strong unless you're going really fast. And we're going to see examples like the amount of things that this encapsulates, the amount of things that you don't care about, and this still works is wild. For example, when an object explodes, like it's a really cool thing. So anyway, I just gave you all that example just to show you all, obviously, if friction exists, it doesn't, I say obviously. We can make an easy example to show friction ruins this. But otherwise, and only works if no friction, air resistance. I'll add that to the slide. We call it if there's no non-conservative forces, i.e. friction and air resistance. That's kind of the only two. Resistance / someone pushing the box. Okay. All right. Fantastic. All right. This next slide. Why is this here? Oh, this was for the lab we did yesterday. So I'm just going to delete that. That was for the bouncy ball lab. Okay. When do we use conservation momentum? If things either start together and split up, or the opposite, they start separately. If things hit each other, conservation momentum, guaranteed. If things hit each other and bounce off each other, and I ask you things about velocity, momentum. Like, immediately your brain should go to that. So either they hit and they get stuck together, or they bounce off each other, or they start together and they split up. That's when we're going to use conservation momentum. If they bounce off each other, mechanical energy is conserved. And we will talk about an example of a problem with that. And the math gets a little mathy, depending on what I give you. We'll get to that when we get to that. Inelastic mechanical energy is not conserved. So, if I throw something like a sticky hand, if I throw some Play-Doh at the wall and it sticks to it, that's inelastic. If I throw a bouncy ball at the wall, that's elastic. Your all's experiment that you all did, the lab we did, was an elastic collision between the ball and whatever surface it hit. I will tell you, it's kind of impossible to have a perfectly elastic collision. You need something really rigid, really rigid. Pretty much always the example that everyone uses is pool balls. Pool balls is like always the example everyone uses. It's actually really hard to come up with an example of two perfectly rigid objects that bounce off each other and no energy is lost. That's just a fun fact. Yeah, it's rough. Newton's Cradle is also a really good one. Leo reminded me of that one. Have you all ever seen that toy that like you drop the ball and it dinks the thing and it dinks the other side and goes dink dink, and it's really annoying? The sound is all like, if you've ever seen one in a classroom and someone played with it, it gets really annoying really quickly. Yeah, that's also an elastic collision. You need really rigid objects, but we can approximate a lot of things. All right, here's a question. I am going to open iClicker so I can actually ask you this question. This question's going to look, it's a lot of variables, but it's not that complicated. Just read the problem, write it out. Actually, write it out on your paper. Not like you could write the words if you want, but like write the math. I have two objects, M1 and M2, two separate objects, which each have their own velocity, V1 and V2. What is the total momentum of both objects together? That is the question. This is just practicing, hey, what's my initial momentum? If I have two objects, each with their own mass and each with their own velocity, I highly recommend, if you're like, man, there's so many things going on, just write it out. It'll make your life easier. Oh, my bad. All right, this question is, I'm going to reset this. I put it on my desk, and then I didn't plug it in. Classic. Thank you for the reminder. All right, now I'm going to test this. I don't know if I have to restart the whole thing. Survey says, yes, I do. All right, delete that one too. Third tries the charm. There we go. That's because I'm okay, great. No, probably not. It's generally if there's anything lost, it's how it switches. Maybe there's I don't know. Cost for students is a major consideration. One of the reasons that shows up that's not terrible. It's cost, but yeah, it's better than textbook. It's better than website. Masters, physics, all those internet. That was free. Yeah, I know it's free, but some of the answers are wrong. Yeah. All right. So y'all got 10 more seconds. And 5, 4, 3, 2, 1. All right, let's draw a picture, y'all. You got object 1. You got object 2. Now, I should have probably clarified here that it's in one dimension. So we're going to say these things are just moving left and right. I don't care which way they're moving. I don't care if they're both moving left, both moving right. You would kind of put those values in accordingly. But you got mass 1, V1. You got mass 2, V2. And what's the total momentum? Is just going to be P1 plus P2. You know, you add them up. All right, what's P1? M1, V1. What's P2? MV, whatever, that thing, M2, V2. And then I'd be very careful. Look at that. Great job, everyone. See how easy conservation momentum is? That's my starting momentum of 2 objects. The only thing that would get more complicated is if you had to split into X and Y. Fantastic. So look at that. That's how you add up momentums. Now, this one's a little bit more, we got the vector signs now. Remember, you can only combine X components. You can only combine Y components. So I keep saying that because it's really important. But this is how you add up all the momentums in the beginning and all the momentums at the end. M times V, M times V, M times V, M times V. It's great. It's really straightforward. There's no other types of momentum. Okay. We're only considering linear momentum. Technically, angular momentum is a thing, but angular momentum, you just do that separately. We'll learn about that maybe. But really straightforward. I mean, you all got that answer right, even though I didn't show you how to do it, because it's not too complicated. All right. If I have 2 objects, M1 and M2, and they get stuck together, what is their new mass? Not a trick question. You got like 40 seconds for this. Is it M1 plus M2, M1 times M2, M1 divided by M2, or M1 plus V1 plus M2 plus V2? All right, we'll close this out in 10 seconds. In 5, 4, 3, 2, 1. Ciao. All right. Look, there's not much for me to write here. You know, it's that one. Okay, so what? Let me check the next slide. Okay. Let's take those two ideas we just talked about. Make certain I don't have a clicker question on it. Great. Let's take those two ideas I talked. Actually, you all do it. That's always more fun, right? I have two objects, M1 and M2, with velocities V1 and V2. They hit each other and get stuck together. What is the equation for the conservation of momentum? Oh, they hit each other, get stuck together, and end up with a velocity of V3. Great. What is the equation for the conservation of momentum? Is it, and this is going to just take me a bit to write, M1, V1, we'll put a 2 there, plus M2, yeah, this is the joy of formatting, equals M1, V3. Great, let's leave that. That's one option. Here's another option. Here's another option. M1. Okay. And then here's another option. V3. I am making it on the fly. All is well. There we go. Change that to a subscript. Change that to a subscript. What a good question. All right. What's the answer? And to remind you all, this is all we're doing. The momentum in the beginning equals the momentum at the end, and my phone is reminding me that it's that time of day. Go, blinky, blinky QR code.
No, let me do that. That's so bad.
All right, a few more seconds. I generally just look around until I see people not scanning anymore.
Does anyone need the paper?
Oh, it's still not working? What a good question.
Oh.
It's the... All right, gonna give you all like 20, 30 more seconds for this. Which one?
fun to look at.
Yeah, it's like it's hard to.
That screen does not exist.
I know. I remember you saying that. She's like, is there
Good question. I think if I was doing it through this, the answer would be yes. But since it's through my laptop, I think the answer is no. Yeah, this I think is tied into the network. I'm only connected to a display port here, so I don't think. But that would be cool. That'd be great if I could. All right, 3, 2, 1. All right, so you got your beginning. You got your M1 with some V1, and you got your M2 with some V2. That's my initial. And then my final is they're stuck together, and we don't know which way they're going to go. Let's just say they go to the right. You would have to do the math to figure out which way they're going to go. And what's the new mass here? We already answered that, so that's not surprising. So it's just as simple as M1 V1 plus M2 V2 equals M1 plus M2 times V3. Now, this last answer is the exact same thing. This last answer is just to show you all it's mathematically the same thing. I kind of put it there just to remind you all. It's as if, when they're stuck together, it's as if you have two objects traveling at the same velocity. Because they are. Because they're stuck together. If you're in a car going 60 miles per hour, you are going 60 miles per hour. So I put that last response there just to kind of show you all. And, a few people picked it, that's fine. They're both the same thing. We generally write it in the third form because it's easier. You would kind of do that if you were solving a problem. One thing I want to point out to you all before we move onward, you can do this problem in reverse and it would work the same. So instead of the objects hitting each other and getting stuck together, you can have the exact opposite. Two objects together and get separated. For example, you can do a conservation momentum problem of you're in a car. You take your foot off the gas, that's important, and somehow there's no air resistance or friction. If you hop out of the car, what happens to the momentum of the car? If you hop backwards outside of the car, if you actually just hop to the side, it's not going to change. Okay, well, I guess it push it. Yeah, this is why you don't stand on a rolling. Look, we all know that rolling chairs are dangerous, right? Like, let me rephrase that. We know that what I'm doing right now is not a great idea. You don't want to stand on a rolling chair to get something. Yeah, and you can think of it in a forces example, but let's think about momentum example. If I jump forward, which way is the chair going to go? Look, that's conservation momentum, y'all. That's conservation momentum. My momentum, right now, what's my momentum? 0. So if I jump forwards, I have a positive momentum. The chair will get a negative momentum and go the other way. Ta-da! It's another way of understanding why that happens. It also explains, I don't know how sensitive and tough. Guns are always classically mentioned in momentum. Why? Because something goes really fast in one direction and they start together. So I'm going to mention this. Guns, when you shoot a gun, it pushes backwards. Newton's third law. For every force, there's an equal and opposite force. But you can also understand that with momentum. You shoot a gun. The momentum of the system is 0 when it's before anything happens. A projectile goes one way. The gun goes the other way because it's going to get conserved. So that's true. Rockets, same thing. Rockets are a conservation momentum problem. You shoot hot gas out the bottom, the rocket moves upwards. It's literally, it's this problem. All the fuel and everything is in the rocket, and then you push it really fast one way, and the rocket goes the other way. And yeah, you actually, what's cool about this, don't really care about why the gas started to get pushed. You don't care about that it's because of a chemical reaction where energy is released and all that kind of jazz. You just care that gas is going fast. That's what's really powerful about conservation momentum. You don't care why the thing happened. You just care that the thing is now moving and the thing will move the other way. That's what's really, really cool about this. It's such a cool thing. So great, look, it's the thing we said about. You all got that down. That's the momentum of an object stuck together. Look how consistent I am. If you're in a car going 60 miles per hour, you're also going 60 miles per hour. It's great. Conservation momentum, really straightforward. The only challenge to conservation momentum, honestly, is do you remember to split it up into X and Y? That's really the only major challenge. Setting up these problems is very much a straight, if you can draw the picture, it's pretty easy to do from there. It's straightforward. I'm going to keep using that word, straightforward. Easy is relative. Straightforward is also relative. All right. Here is a bunch of examples. I highly recommend not having these like memorized. You can build all these yourself. If you have two objects and they bounce off each other, you got the momentum of object 1 plus the momentum of object 2 equals the momentum of object 1 at the end plus the momentum of object 2 at the end. Like, these are not equations you want to memorize. I give these as examples. The reality is you could have 10 objects and you just keep adding it. This is just to give you examples of what these look like. You all built this one. That's the clicker question I just gave you. And then the one below it is just the exact opposite. Instead of them coming together and getting stuck, they started stuck and they split up. So these are not like equations to write. These are not going to be on the formula sheet. They're not going to be. I even don't recommend you look, if you really want to, put them on your note card and all that kind of jazz. But the reality is all you need to solve conservation momentum is this equation. All the momentums I start with equals all the momentums I end with, and maybe you also need the equation for momentum. That's the only two equations you really need for these problems. That's it. And you just build the equation, just like we do with conservation of energy. You build your own equation. And that's all we're going to do today is just practice a bunch of examples of that. Like, that's why I said we might actually get through this today, because at this point it's just practicing. I taught you conservation momentum. Taught you, and I've shown you the equations. That doesn't mean I've taught you how to actually do it. Okay, so here's how you solve these problems. If there's a collision, use conservation momentum. Draw a picture, beginning and end. Identify what type of collision are they ever getting stuck to each other? That's basically what you just need to ask yourself. Are they ever getting stuck to each other? Is that in the beginning? Is that in the end? And then you just go through the classics. What's given, what's missing. Write down the two equations. P equals mv. And the sum of pi equals the sum of pf. Build it and do it. There is only one type of problem in conservation momentum that is very unpleasant, and it's an elastic collision if I don't give you the final velocities. We'll do an example today, and I'll show you why. And it's not because we'll see. We'll see it when we see it, okay? The setup isn't bad. Doing the math gets a little tedious, we'll say. It's very mathy. All right, but we'll see it when we see it. So let's not worry about it till we see it. Okay. Two figure skaters are coasting in the same direction, with the lead skater moving at 5.5 meters per second and the trailing skater moving at 6.2 meters per second. When the trailing skater catches up to the leading skater, he picks her up without applying any horizontal forces on his skates. That's important. He's not making himself go faster. If the trailing skater is 50% heavier than the 50 kilogram leading skater, what is the speed after he picks her up? What a paragraph. Go through the steps, y'all. Draw a picture. Write down your givens. Start there. Organize your information. Once you have the givens and the picture, there's a collision happening here, y'all. They hit each other. They interact with each other. We call that a collision. So it's going to be conservation momentum. So try it out. Try out steps 1 and 2. I'll go around. Feel free to move onwards if you're good past that. But after I see everyone get past 1 and 2, I'll do a checkpoint. And then you all can try solving it. I'll put the answer up here as well. Oh, it just smells bad. Nice. You get an aromatic experience. How good.
Yeah.
This is why group work is so important. To catch stuff like that. That's like super easy to make those.
Did you get a different number?
kg is about 2.2 pounds. Yeah. No, you're fine. You're fine. I'm like, what the heck is that? You work on whatever you want to work on. And which one?
So it's
No. What are we solving for? Fine. Make it find out what's your final decision. What is the solving? What is the yeah, we're solving.
Oh my god, I want to talk about this so bad because I'm like, what?
Build the equation. Build the equation. Everything worked great. Okay, so just to give you all some checkpoints, let's write down our givens. Y'all tell me, what are they? We got mass. We got the mass of two things. Let's call one the trailing and two the leading. So, the leading one's pretty straightforward. It's 50 kg. What's the trailing one if it's 50% heavier than that? 75. It is heavier by 50%. So multiply the M2 by 1.5. All right. And then you got V1 is 5.5. So, nope, that's wrong. Trailing. So this is where you need to be careful. If you make a mistake on these problems, it's probably going to be in identifying these. Oh, and also notice I put V1 here. I need to put V1 initial, V2 initial. You need to clarify that. If you just put V1, then you're going to say that they're moving at constant speed forever. Your notation matters for you to actually understand what you're doing. Look, if you just put V1 and you in your head know what that means, sure. But remember, your heads forget things. If your brain hasn't failed you yet, it will. So good notation helps prevent silly mistakes. Good notation helps prevent silly mistakes. A good example of this is if you ever do programming, write good comments. Like if you haven't learned that yet, comment your work really well because you might know it now. You're not going to remember it 5 months from now if you ever want to reference it. Or if anyone else ever looks at your work, you want them to actually be able to understand it. These are good practice. Notation is important. Okay, step 2. What are we solving for? VF equals question mark. Oh, and let's draw a picture. Here's person 1. Here's person 2. There they all in all their glory. And then the final, they're stuck together. Okay. There is a collision. So what are we going to use? It is going to be an inelastic collision. What's the overall concept that inelastic collisions use? What's the math? Conservation of momentum. The sum of my initial momentums equals the sum of my final momentums. They are vectors. We are blessed that this is a 1D problem. Don't worry, I'll give you ones that aren't. I know you were worried about that. And if you haven't already, y'all just set that up. Build the, actually let's do that in step 3. Build the equation. What momentums do I start with? What momentums do I end with? Set them equal to each other and do math. If you haven't already done that, I'll give you a little bit of time and then I'll do it. If you got it, feel free to move on to the next one or whatever else you want to work on. I have a little bit. Not a little on the next slide. That's what we're going to do next. There's one more again, by the way. Was it the final math? So I'm not even going to, when I build the equation, I'll just call it 1 plus 2. Like if someone's taller, will they weigh less?
What if you were like 5'2"?
So it wouldn't matter. It would not matter for linear momentum, the only variables we care about are mass and velocity. Now, angular momentum, like rotation, stuff like that, then you start to care about the length of the various things. So like part of this problem, if you're trying to pick someone up, you will start to like move in some direction. That's a rotation, and that's where you have to consider angular.
Oh, okay.
So we're going to assume these are perfectly rigid bodies that fix her up. Yeah. That there's enough torque acting on that it doesn't fall over.
He was calling me back, but
Yeah, I mean, and you can do the math. You can do the math here. 1 kilogram is 2.2 pounds.
yes,
Gosh. How are y'all doing? Okay. All right. So let's build the equation. So they start separated. So you got the momentum of person 1, and then you got the momentum of person 2 equals, at the end they're together. M1 plus M2 times V final. We built our equation. That's the key to this. Conservation of energy, conservation of momentum. It's a build your own equation situation. And then you just put in the numbers, y'all. So the mass of person 1 is 75. So 75 times 6.2. Do note that positive direction matters. These are vectors. If someone's moving to the right, is that positive or negative? Positive. If someone's moving to the left, positive or negative? Negative. These are vectors. We care about positives. We care about direction now. Don't forget that. In this picture, they're moving the same way. So we call those positive velocities. I'm going to put little pluses here just to denote that. You could say everyone's moving to the left and everything, all the negatives would cancel and it would work out the same. But I do want you all to know that. All right, so 50 times 5.5. And I will say these equations get a little long. 50 plus 75 times VF. Y'all tell me, what's that left side equal? I don't have I can get my calculator. Someone has to have plugged it in, right?
What do you ask?
What's the left side of the equation equal? 740, so that equals, okay, I can at least do the right side. And then if you divide those numbers, I'm trying to do my due diligence of fully solving the problem. There you go. I think it's like 5.92 or something. Yeah. If you want the extra 2. All right, fantastic. We're okay. Onwards. A boy sleds down a hill and onto a frictionless ice-covered lake at 10 meters per second. In the middle of the lake is a 1,000-kilogram boulder. When the sled crashes into the boulder, he is propelled backwards from the boulder. The collision is an elastic collision. If the boy's mass is 40 kilograms and the sled's mass is 2.5 kilograms, what is the speed of the sled and the boulder after the collision? And I think we have entered into an elastic collision where we will discover there's an extra step we have to do in this problem. We're going to discover what that extra step is when you'll solve this problem. As you solve it. Yeah, so there's going to be 2 unknowns here. That's kind of the... But go through it as normal, y'all. Go through it as normal. Write down your givens. Build the equation. I want you all to discover that we need something extra that we didn't need in the last problem. And we're going to assume that the boy stays attached to the sled the entire time. The boy is always attached to the sled, otherwise this problem is impossible. It is a perfectly elastic collision. Perfectly elastic. If I ever say it's elastic, you can assume the word perfect. Yeah. It can move. It can move. It can move. No friction anywhere in this problem. There's friction. Well, it might not go fly, but it will. Again, in the real world, there's a little bit of friction. In the real world, this happens. But we took this problem in space, which is actually they had a tiny little bit. It's called the Darkvision. They did semi-crash relative to a giant.
I need to like.
So in space, you could have slightly zoom in. Do it soon enough.
No, this is. Oh wait, no. There was one.
Because it's perfectly elastic. Elastic means you bounce off.
Yeah.
No, you stuck to the sled. That's it. Otherwise, we're gonna assume. You can't assume the boulder in the beginning is not moving. We're assuming the boulder in the beginning is not moving.
I wonder how a 1,000-kilogram boulder's on top of an ice-covered lake.
It's a very thick sheet of ice. The entire lake froze. Yeah, if they're attached together, there's one spot. Yep. All right, so let's build this problem. Y'all tell me what's given. Well, actually, here, look, let's draw a picture. There's a boy. He's moving. Here's a boulder. There it is. That's my initial. Final. final. Which way is the boy moving? Left. So which way is the boulder going to move? Okay. So this is V1 initial, this is M1, this is M2, this is V1 final, this is M1, this is M2, and this is V2 final. Okay, y'all tell me what's given. Mass 1, what is mass 1? Yeah, mass 1 is not 40, it's not 2.5, they're stuck together. So let's just go ahead and make our life a little easier. All right, what else is given? Velocity of the kid, V1 initial equals 10 ms. Beautiful. What else? Yeah, we got the initial velocity of the rock. All right, anything else? No. What are we solving for? Oh, we didn't put the second mass. Thank you. M2 equals 1,000 kilograms. That is a ton. All right, step 2. What are we solving for? Both final velocities. V1F equals question mark and V2F equals question mark. Step 3. We are going to use conservation of momentum. So we're going to do sum of momentum initial equals sum of momentum final, and P equals MV. And I'm actually going to move step 3 over here. So if you haven't done this already, try to build this equation. I'll give you all like a few moments to do so. You're going to find there's a problem. So we get M1 V1 initial plus M2 V2 initial equals M1 V1 final plus M2 V2 final. We're at least blessed that this term goes away. That's good for us. Can I solve this equation? Why? Why can I not solve this problem? 2 unknowns and 1 equation. If you'll ever have 2 unknowns and 1 equation, how many equations do you need for 2 unknowns? 2. So the question is, what other equation can we make? And so to that end, I'm going to remind you all of a definition I gave before. And it was kind of hidden in here, but this problem helps us remember it. Where is it at? Somewhere up here. Boom, boom, boom. Here it is. Energy is conserved. In an elastic collision, energy is conserved. I.e., just reword those problems. Reword that wording. Conservation of energy. So this problem is not just a momentum problem. It is an energy problem. So I will remind you of this equation. Energy initial plus any work done by friction or anything else like pushing, all that kind of stuff, equals energy final. Is there any work done? Is there anything pushing? Is there any friction, any air resistance? So my question to you all, build this equation. What energies do I start with? Energy/energies. What energy/energies do I end with? Build this equation. No, you don't have to integrate. You don't have to integrate. No, yeah. I didn't want anyone to hear that stuff freaking out. No integrals. But you will have to do some messy algebra. last equation. You have to get it. There's no getting around this. There's no way around this. There is no other way of solving this problem given the information you have. That I know. Where have I not checked in at? Alright, so y'all tell what energies do I start with? Good. And then what energies do I end with? You tell potential, there's two types. What are the two types of potential? What type of energy does this pin have right now? Yeah, it's not a trick question. One's through gravity, one's through one's through gravity. How does something gain potential? How does something gain gravitational potential? Like if I wanted this thing to gain gravitational potential energy, what would I do to this? Which way? I have to move it. Yep. Yeah. As you lift something, you're storing energy. And then the other one is a spring. That's fine. Does anything go up or down? So there's none of that, so it's just, are things moving? So that's your checklist. Anytime you all think about energy in this class, it's just a checklist. Did something move up or down? If so, it's got gravitational energy. Is there spring? If so, it's got spring energy. Is it moving? If so, it's got all right. So what type of energy do I start with, y'all? There's a checklist. What are my three types of energy? Kinetic. What's another type of energy? Potential due to, there's two potentials. Gravity and spring. All right, we go through our checklist. Are there any springs? No. Is this thing going up or down? No. No gravitational potential energy. Is it moving? Yeah. So 1/2 m1 v1 initial squared. That's the only energy I start with. The boulder ain't moving. It's got nothing. Equals, what energy do I end with? m1 v1 final squared plus 1/2 m2 v2 final squared. Whether you like it or not, we have built two equations with two unknowns. Good news, you can get rid of the halves. It's slightly... I'm going to do this on a new slide. Okay. So what's the end result of this? What was the whole purpose of this? Let's take these two equations and just write them a little bit cleaned up. M1 V1 initial equals M1 V1 final plus M2 V2 final. Great, that's one equation. Let's take this guy, put it right here. M1 V1 initial squared equals M1 V1 final squared plus M2 V2 final squared. It is two equations and two unknowns. So step 4, plug in numbers, y'all, and do some algebra. I will show, like I've just put the numbers in. 42.5 times 10 is going to equal 42.5 times V1 final plus 1,000 times V2 final. Great, that's one equation. I'm just plugging in numbers. 42.5 times 10 squared equals 42.5 times V1 final squared plus 1,000. You all got to do some algebra. Solve for one of the variables. It's a system of equations. I want you all to struggle through this algebra. This is a math problem at this point. It's literally two equations, two unknowns. Isolate one of the variables in terms of the other variable, plug it into the other equation, do some math. It's not the most. This is why I told you all elastic collisions have some math grossness to them. Mm-hmm. Yep. Good. Yep. Equals. What energy final do I end with? What's the equation for it? What types of energy do I end with in this picture? So in each object has a kinetic energy. Or the sled has kinetic energy. So that's where the 1/2 m final square comes from. Plus the kinetic energy of the boulder. 1/2 m.
I mean, he doesn't.
Final square.
I said that really well.
Oh, what? I didn't actually.
I said the professors here suck, but
Oh,
you're one of
thanks.
the ones who don't suck. You're the only one.
You're fine.
You're genuinely like the only professor I've had where I'm like, oh, okay, like I'm actually learning stuff. Like I actually feel like I like don't feel like I'm doing.
Yeah, no, the bar is low at college as far as teaching well.
That's fine.
Unfortunately.
That's fine. I'll get through it.
Unfortunately. Yeah. Yep, good. That's good. Yep. And then you're gonna take that into equation. Yeah, it's unpleasant, but you can do it. Oh, I'll give you all the answers. The boulder does move. Like, so at this point, it's an exercise in algebra, which is a skill set that you all, even though it's not one that like is it's one you all just need. All your all's majors, you all got to be good at math. That's just the reality. This will not be the last class that you see math. If you're stumped, call me over. Or Leo. Or Angelina. Or anyone. Nope. Nope, hold over. That's fine. Yeah. This is why we had to build 2 equations. Because this equation, same thing happened. This term does go away, and these are initials. This term goes away, but we don't know this, we don't know this. So we can't solve this as is. We had to build another equation. It's unpleasant. It's mathematically possible. What happened? Yeah, you got it. Yeah, I was like, there ain't no one gonna do it for it. Okay, I say that. I will kind of sort of work this out. But yeah, it's just an algebra problem. Y'all just gotta grind it. When you all get to statics, if you take statics, you're gonna be doing this a lot. Systems of equations. From what I hear, statics is just a bunch of systems of equations. Are you plotting it? Yeah. That's a strategy that works. I will show you all. I'm not doing that. Turns out but yeah, this is just show you elastic collisions, ironically, are the worst ones. If I don't give you both final velocities. Or either of them. What happened? Did you plug it back into that one? Oh, we plug it back into the equation that you got it from. Yeah, you got to plug it into the other one. Yeah. All right, so just pick your poison. You can solve for either variable. I'm gonna pick like this first one. So I get 425 equals 42.5 V1F plus 1,000 V2F. And then I'm going to solve for V1F. There's no better way of doing this, y'all. It's going to be like, if you just do this, it's easy. No, there's not like a magic technique here, y'all. So the next step is 425 minus 1,000 V2F equals 42.5 times V1F. And then I divide this side by 42.5 to get rid of that. So I get V1F equals 10 minus, I don't know what 1,000 divided by 42.5 is.
23.5.
Whoa, what was it?
23.529.
23.529. I'm just going to put 5.3. Great. And then you have the pleasure of plugging that in right there. We're going to take this and put it here. And then you get to square it. And then you get to do a quadratic formula. Yeah. All right, so let's just do that because it's fun. Look, this is not the part of physics that's fun because it's not physics. I mean, you have to, yeah, it's not physics. Like, this is math. But the reality is you all need this skill set. Like, and to be honest, if you're doing this if you were actually doing this for like a company or stuff like that, I would honestly just like find a thing online that would do this math for me. But you need to know what the heck the thing's doing. That's kind of the exercise in doing these at this point. That's the reason for it. So great. Orange goes down here now. So let's now do orange. We're going to take this equation. So I get 10 squared is 100. So I get 4,250 equals 42.5 times 10 minus 23.53 V2F squared plus 1,000 V2F squared. So 4,250 equals 425. Nope. 42.5 times 100 minus, I'm just going to get a calculator. Ten times that times 2. 470.6 V2F plus this thing squared plus 1,000 V2F squared. And then 4,750 minus. Oh, that's a nice number. That's weird. I like that, though. I'm not going to worry about the 0.5. 23,530. All right, almost there. So move stuff over so we get 0 equals 500. V2F plus all right. And now you do quadratic formula. And I'm going to hope I didn't make any math mistakes along the way. Okay. This is the part where I tell you all I am not going to have you do a problem that takes this long mathematically on a test. Okay? But huh? Probably not. Probably not. Now, so there's two things I'm going to show you. One, and then you do quadratic formula, and at this point, negative b plus or minus the square root of b squared minus 4ac all over 2a. What are we at time-wise? Sure, I will do that. I will do all the things just to show you all it all works out, or to show you all that it's really easy to make simple mistakes somewhere, and then I have to find my mistake. It's going to be an exercise in one of those two things. But I don't have enough room. Oh, thank you. Is it actually better than I thought? Yeah. No, that's good. Once this erases, I think we actually get to avoid the quadratic formula. Once my computer says that this operation I did is acceptable. All right, I made a mistake, y'all, because my notation was a little off. This is 4,250, which this is great news for us. This problem's not that bad. We don't have to do quadratic formula. One of these goes away. You can get rid of, they both have a V2F in common. Yay. You can't factor it out yet. If the constants don't cancel.
Oh, yeah.
Yeah. So you get negative 20,000 equals 24,530. Fingers crossed I didn't make a mistake somewhere. Oh, so good. Very, very important. Negative. The math comes out as negative. The math tells you, we'll give you that negative. Yay, we did it. Look, the answer's over here somewhere. 0.815. It is 0.815 in my calculator as well. So actually, this isn't terrible. This is a good, look, if you all haven't done a problem like this in a while, I do encourage you to actually do this math. Because this is a skill set. Being able to do a system of equations is one of those skill sets that mathematically you all should be able to do. Like, it's a foundational skill. It's a foundational math skill kind of thing. Like, this is, systems of equations are learned in, gosh, some part in high school. Like, I don't know when. How good are you at algebra is basically what this problem tests. This kind of math. And I don't know. I feel like it's important. I have to think about why it's important more in detail. I think the value of being able to do this is to be able to do a bunch of math steps in a row without making a mistake. As silly as that sounds, like, you got to make certain you don't make mistakes. And this has so many steps in it You all are going to do a bunch of math in the future. You got to make certain you're not making mistakes. This is an exercise in being careful.
How did you get 470?
Where?
The second step.
Yeah, so I got. Yeah, it's boiling. It's boiling. Okay, that 470 comes from boiling. Yeah. It's good though. All right, and then the good news is once you have this, if you're like, man, I don't want to have to do this all again for V1F, you don't have to. Just plug that in there. Yeah. What color are we going to use for that? Purple. If you just follow the arrows, this is a chutes and ladders situation. All right. So V1F equals 10 minus 23.53 times negative 0.815. Oh, why is my boulder negative?
The 20,000 negative was.
Did I not? Oh, I lost my negative, y'all. See, look how silly this is. Great catch. Look at our picture, y'all. Again, this is an exercise in being careful, and I wasn't careful. Check it out. Which way is that boulder moving? Yeah, that boulder is moving to the right. Did my answer get a positive number? No, because look right here. If you're like, where did that mistake happen? The mistake happened between this step and this step. I dropped a negative.
Oh no, he just forgot the.
I forgot to put a negative here, which means I forgot to put a negative here, which means that's positive, which means that's positive, which means that's positive. And how do you catch this mistake? You don't catch this mistake by going through all your math and saying, is everything perfect? You catch this mistake by realizing the final answer was negative, and that doesn't make sense. It actually isn't that much work to check this mistake. It's looking at the final answer and saying, I didn't do that step. I did not think. Does this answer make sense? Does it make sense for my boulder to move to the left if someone hits it? No, that's nonsense. That's like me running into this chair and the chair coming back at me. It's nonsense. But we will find that V1F is negative because the kid does bounce off the boulder. If you plug this into the calc, I will do it just to do my due diligence. You get that the kid moves back with a velocity of negative 9.18 meters per second. Woo! Okay. So there you go. Good exercise of being careful. Is there something wrong?
On the fourth line up in the orange, you didn't. It wasn't a math error, but you missed the squared on the 1000 V2F.
Thank you. That'll confuse people. Yes, thank you. No, it's good. If people look at that later, they're going to be confused. Good. All right. So we did it. At least I did it. I don't know if you did it. Look. Yes, I know this takes a bunch of time, but if you haven't done a problem like this, it is worthwhile to make certain this is an exercise in sharpening old math skills. This is an exercise in sharpening, can you do a long, extensive problem? I'm going to go ahead and tell you all, as you get into your future classes, I don't care what major you are, if you do math in future classes, you're going to do problems that take an entire sheet of paper, if not 2 sheets of paper. That's going to happen. Any engineering student in here, computer science, your example is you're going to write a code that has hundreds of lines. If you're an engineering student or anyone that's doing any kind of math, you will do problems that exist across multiple pages. Can you be careful? Can you make certain you're being careful? And this is why working with other people is important. Because if it's unlikely that both of you will make a mistake at the same spot if you make a mistake. So it's one of those, that's how you can check. And if you don't believe me, just ask literally anyone in any future class and they'll tell you the same thing. Your TA, TA can speak from experience. Yeah. What's the longest upper level under? Do you have good memories of doing quantum mechanics,
Mechanics, I'd say like 3 to 5 pages.
Yeah, there you go. Again, that's from a physics major perspective. Talk to some engineering majors and you'll experience the same thing. That's how it goes. All right. Now, before we go into the break, I want to point you all. I'm actually going to take this slide and I'm going to move this up. I am not going to spend the time deriving this. So this is what you all just built. You all built these two equations. This is an elastic collision for two objects in an elastic collision. So great, you did this, you built this equation, and then you all built this equation, like this is conservation of entry, conservation of momentum. If you do a bunch of clever algebra, you get the bottom relationship, which is really nice. And this is, again, I'm not expecting you all to know this bottom equation, I'm just mentioning it to you all. It's like a little shortcut. If ever in a future class you all need to do this, this is a shortcut. It turns out if you add the initial velocity of 1 to the final velocity of 1, it equals the final velocity of 2 plus the initial velocity of 2. And you can actually just use that equation. So you can use this equation and then this equation down here, and it's much easier. There's a video about this derivation because it takes them like a few minutes to show this. So I'm not going to spend the time because it's a bunch of like math tricks. But there you go. We'll go ahead and into the break. I'll leave this up. And after the break, we will solve, I think we just have two problems. And then I guess maybe I'll start talking about gravity a bit. I don't know. My thought processes were here. If I can get stuff done, I'm not going to tack more stuff on. It'll just give us more review days before a test. So anyway, we'll do a couple more problems and then see where things are at after a break. But take 5 minutes. Rest your brains. What's up? I got you. Leo. Over here.
Yeah, I just wanted to know.
You forgot the springs. Because you don't plug it back into the original. So you're taking this.
Is it not
Alright.
I am.
Yeah. So you solved for V final sled from this equation. You don't want to plug it back into the equation you solved it from.
Oh,
You end up back in the same spot you started with. So you should find, you want to plug it into the other equation. Yes.
Oh,
Yep.
okay.
Yeah, if you have two equations that you want to, and that's really common. I've seen a lot of people doing that. You don't want, if you plug it back into itself, you're just going to find zero.
Yeah. That makes so much sense. Thank you.
Yeah.
Okay, so
Is mechanical not conserved in elastic?
No, because they squish. There's energy lost in that squishing. As heat.
If it's like perfectly inelastic, then
Yeah, it doesn't matter. Yeah, it's not. Easy example. Two objects hit each other, and they're traveling at the exact same velocity and the exact same mass. If they hit each other and get stuck together, they stop.
because it's a V squared final, doesn't matter even if that, because
Yeah.
if you have an M1,
if you have two objects traveling towards each other,
you can never have a zero on the other side.
Yeah, that's why. So, inelastic energy totally is not conserved.
Yeah.
It's only if they perfectly bounce off each other. And the idea there is they're bouncing off each other like a spring.
Mm.
It's as if an object hits a spring and bounces off it. Yeah. But it's a cool thing that in inelastic, it does work. And anything in between also works. You can use conservation momentum for any problem, whether it's like slightly inelastic or it doesn't matter. It doesn't matter if they get slightly stuck together and then still move past each other, you still get the same result. It still works. As long as there's no friction or air resistance or like things externally, as long as the energy is maintained in the system, doesn't matter. It's cool.
was gonna ask if you're teaching physics too.
I am not. I got my schedule. I am teaching Physics 1 for non-engineers. So I'm teaching 2053.
Yeah. And do you know like any of the teachers that teach statics? Or no?
I don't know like anything outside the physics department.
Do you know Costas?
Yes. So Rate My Professor is use Rate My Professor to determine.
Yeah, it says he's a lot of bad ratings. My brother took him. He says it's just a really hard class.
Okay.
Like he's just a hard professor.
Rate My Professor and other people's experiences are always the best way to determine. That's always what I kind of point people to.
Yeah. What was yours again? What was that? The comment that you had?
Oh, the Millennial Bill Nye, that one or Bill?
You got it with the
Yeah. So. Yep, Rate My Professor is a great. It is fairly accurate because it's an average of a lot of people's experiences. So it tends to give you a fairly representative. So the average.
Several I took this. So I think yeah.
All right. So let's keep this train rolling. All right. Reminder to y'all. If there's an X and a Y component, I've said this like 5 times now, and I'll keep saying it because it's really common. If you have an X and a Y component of velocities, you gotta split it up, y'all. You gotta keep them separated. They're vectors. They are vectors. So you gotta do all the X's together, all the Y's together. If it was really a fun problem, all the Z's together. Don't worry, I won't let you have that much fun. So, case in point, look, it's a bird. Yeah, so we got a falcon diving at 28 meters per second at an angle of 35 degrees. And it catches this pigeon. And they're BFFs, so they hug. And they stay attached. Yeah, it's just catching its friend. What is their combined velocity after impact, after the pigeon gets tagged? If the pigeon's initial velocity was 7 meters per second directed horizontally. Again, what's really cool about this momentum stuff, you don't care what happens in the collision. You don't care whether or not they like tumble or whether or not they like it doesn't get a good grip at first and then it gets a good grip afterwards. You don't care how long that collision is. You don't care about any of that. All you care about is the initials and the finals, and it works. And this is not like ignoring. All we're ignoring is air resistance. We're not ignoring everything else. You just don't care about everything else. That's why this momentum stuff is so powerful, so useful. You don't care what happens during the collision. You don't care how messy that collision is. As long as all the pieces are accounted for. Yeah, try it out. Have fun. I'll walk around and assist. Givens, missing. I drew the initial for you. You need to draw the final. Take a guess of what it's going to look like.
I know that what he's saying.
And this one is just I actually just
Okay, that's not what I said was.
One reason is what's the equation for the original?
Yeah.
So you need to conserve that one half. So when you pull out the constants, you need to hold in front of that one half. Otherwise, you're saying it be squared out. Yeah, so it's a little subtle. Yeah, it's a little subtle. It's a good question. Yeah. Yeah, it's not too bad, but it's one of those.
Oh, you know what? I think this.
Yep. Oh yeah, you get 3 substrates. Yeah. You can put them all next to each other. You don't need to like do a cascading downwards situation. Yeah, it's You would also. Yeah, they're much, but they're not as fun. That would be. And I will say, if you press far enough, so you get a good job. Person. Stop doing it lower. Right. So you still you're managing. You know, it's good management. The benefit you're managing the ladder. They end up being like this.
Yes. Okay.
There is
We're doing something.
how it is.
So I think instead of like the strawberries, this would be like one fluff. It's the longest I'm
Yeah, I don't know. Business, sure, whatever's easier. But man, engineering's fun. You get to make things. So I'm just going to write down the givens if you haven't done it already. We're going to call the Falcon 1 and the Pigeon 2 because that's what's labeled. So mass of 1. So M1 equals 0.9 kilograms. M2 equals 0.325 kilograms. And this is immediately, you should look at this and say, oh, there's X and Y components. There's an angle involved. There's X and Y components. So V1I initial, sure, the magnitude of this is 28. But honestly, you know what? I'm not going to even put that here. I'm going to put this. V1X initial. I am immediately going to recognize I need to split things into components. And I'm going to do that immediately. Again, if you recognize something like this, do it sooner than later. Why wait? So in this case, we draw a triangle. There's my X component of V1 initial X. Yes, we get all the subscripts. I warned you all of this, like, if y'all remember, I warned you of this way at the beginning of this semester that you're going to get all the subscripts. We never reached that point. And you need all three of them. You need to know that it's a velocity of object 1 initially in the X direction. Also, when you all draw this triangle, you need to draw arrows. I can almost guarantee bet that a third to a half of us messed up the Y component of this. I don't know. If I was a betting man, I'd bet on that. I don't know that for sure. And maybe I'm underselling you all. V1 initial X is going to be 28 times, according to our triangle, cosine, because we want the adjacent side. Fantastic. That's, I don't know what that is. It is, wait, what'd you say it was? Oh, 23.94? 22.94. Let's just ask this question now. Is it positive or negative, the X component? Why? It's going to the right. What about when you all do the Y component? If you just do the math, if you just write 28 times sine of 35, and you say that the answer to the Y component is 16.06, it's wrong. That's wrong. Because of something very, very, very important that you need to remember with vectors. The direction, the sign of the vector comes from the picture. Which way is the Y component, up or down? The math will not tell you that. The math will not tell you that it's negative. And if you mess up this negative, the final answer is going to be wrong. If you don't put the negative, you've instead drawn a picture where the falcon is coming up from the top, and your final velocity in the Y direction will be up. And again, it may seem tiny. It may not seem like a big deal, a plus sign or a minus sign. But if you're designing a rocket, you want the rocket to go up, not down. And that's going to matter. Like, it seems stupid, but I can almost guarantee you lots and lots of money has been lost in this world because someone misplaced a positive or a negative sign. I mean, financially, literally. Like, financially, that would be true. If you're in accounting, that's very much true. But in building stuff, yeah, if you forget a plus or a minus sign and you do a bunch of programming of something, that can be really bad. At worst, you lose money. No, not at worst. At best, you lose money. At worst, someone dies. Like, yeah, right? A positive and a negative sign could be a life or death situation, as silly as it sounds. So we got to be careful. It could be, depending on what you're building.
Are you asking for the vector or just
Yeah, that's a good question.
because the negative wouldn't matter?
Yeah, I do want the vector. I do want the vector as the final answer because I think it's more interesting. I think in the problem set I give it to is the magnitude, but give me the vector, the x and the y component of it. Yeah. I want to find my final answer. I want the so step 2. What are we solving for? We are solving for the final, and I want that in terms of I and j. I want an I hat and I want a j hat, and you all can guess that. Which way are they going to be moving at the end? To the right or to the left? Yeah. Which way are they moving? Yeah, up or down? Again, you can check your answers, y'all. You don't have to do any math to know that they're going to move down. You can tell that from the picture. That's not always going to be true, but in this problem it will be. In this problem, you can pretty straight up tell that's going to be the case. So, try it out. I don't actually know what the final answer is. Let me figure it out. Let me see if I can find it. I can get it from that answer. I'll let you get stumped. Yeah, it's perfect. Yep. Yep. You would just want to put D1 initial X, D2 initial X. It seems silly, but it's one of those. I realized afterwards. Yeah, that's fine. So you got the X. Yep. Good notation will benefit you in the future. So to give you all another checkpoint, X components, Y components. So we have M V1 initial X plus M V2 initial X equals M1 plus M2 times V final X plus M. All we did to build these, this is the same thing we did. This problem is the exact same problem that we did in the beginning. Where is it at? It's this problem. Now you just do it in 2 dimensions. It's the exact same problem. You all set up this part at the bottom. It's that, but do it twice. Do it for the X, do it for the Y. You had so much fun doing it once, do it twice. Everything builds. Yeah, I put it at the bottom because I'll work it out. And just think, y'all, if I showed you this at the beginning of the semester, think how gross it would look to you. But now look at, this is an indication of how far you've come. When you can look at this and it's like, I can understand what's going on. That's a reminder to y'all. If I had given you these equations at the beginning of the semester, you would have been like, that looks like another language. Look, you're learning the language. This is hopefully some level of encouragement to you all. Think back to how little you knew maybe at the beginning and how much you now know. That's within like 0.2% or something. It is. Yep. Yeah, that's how I generate these answers, actually. I generate these by looking at the answer going backwards.
Why did you get it?
Yeah, and that's the
Yes, I know for sure it should equal that because I actually use that to get those two.
You're okay.
All right, so step 4, we just plug in things. Do you want to have the pleasure of doing step 4? You're welcome to. It's the worst step.
Yeah.
No one wants to do step 4. Oh, it's terrible. Again, the good news, if you're a physics major, step 3 is where you end the problem, basically. You like divide the M1, M2 over, and you say, that's good enough. Someone else can plug, engineers can plug in numbers. Yeah, so, yeah, here we are. Step 4 is the worst part. I hate, numbers are a messy. Oh, I forgot to put something on here. V2 initial x equals. There we go. I didn't write down all the givens, but when I was solving the math, I realized, what's the initial velocity in the x direction for object 2? And in the problem, it's going to the right at 7. And fun. All right. Oh, goodness. And this problem? Don't. Oh, I don't know. We're going to see. I might throw out the idea of it, but we probably won't get too far in it if we do start it. All right. Great news, y'all. Our answer's right. Have fun. I'll be here doing math. Close enough. All right, some rounding happens somewhere, but that's good enough. All right, so great, we got our answer. If you wanted to go a bit further, you could find the magnitude. The magnitude of the final velocity would be the square root of those. Square root of 18.711 squared plus negative 11.8 squared, and you get 22.1. It's 22.1? Great. If you wanted to go even one step further, you could find the angle of this. You could draw a pretty picture. This is just good vector reminder, y'all. Vectors aren't going to go away in your life. Sorry, y'all. The world is in 3 dimensions. As engineers, you can't ignore those dimensions as much as we might want to pretend like they don't exist. Yeah, that's true. If you're clever, you can ignore some of the dimensions. So we're going to move this up so I have room. If we draw a picture of this. So we draw a picture of this because we're really good at drawing vectors and we totally remember all that stuff. We draw a vector that's 18.71 to the right. We draw 11.8 down. So this is my VFX, VFY. This is my V final. If you want this angle, the angle is going to equal tangent inverse of 11.8 divided by 18.8, 18.7. It will equal, what, 35 degrees? 32.2. 32.2 below horizontal. You got to clarify. You can't just say the angle is 32.2. From where? From where the heck is it 32.2? From the y-axis, the x-axis, above, below? Below horizontal, positive x. All right, great. We're having so much fun. Let's take attendance. Forgot to close the last attendance. Great new attendance. Doesn't want to. And we got one more problem we'll go through, then we'll probably dabble in universal gravity, introduce the idea of it, and then we'll go from there. Do you want to facilitate? Do you want to start talking about universal gravity? This is your wheel. Like, it's just as spacey as we're going to get in here.
Like, what way?
I'm not sure.
Go for it.
The relation that follows?
Nah, just like introducing it to people.
There it is.
So I've got my slides you can kind of work with, or you could, kind of up to you. Today we'll just be introducing the idea of it. And again, I have my PowerPoints, just kind of go through it. And we will go, because there's like some good questions. So at some point we'll go through those. But you're welcome to lead some of that.
Yeah, I guess we can just say mutual attraction and then deriving that from I don't know if that's too much to do.
Because
Yeah.
you get equation.
Yeah, you'll have to get to the, you have to
Oh,
get to the
okay.
equation.
So just not the equation.
Yeah, so introducing the idea of always 9. It's up to you. Again, I got the slides. You can kind of just go through those and see what develops. They're in the Files tab. Yeah. Well, that's good. This gives us time for center of mass. Oh, and I need to check carts for the next lab. We're supposed to have carts that have magnets that let them bounce off each other, and then a side that lets them stick together. I want to check that before.
I think people know about like Berry Center. Like Earth Moon Berry Center. Like Berry Center. Do you think people know about that? It's a good example of neutral gravity. Because people think the moon orbits around the Earth, they go orbit around it. It might be too much. I don't know. I don't want to confuse people.
All right. I think everyone's good on this. If not, talk to Leo.
Anybody need it? Attendance?
All right. Last momentum problem. Last momentum problem. 3 deer are standing on a flat rock on an ice-covered pond. A gunshot goes off and they scatter. Deer A runs 15 I hat plus 5 J hat meters per second. It's a really fast deer. Remember that's about 30 miles per hour? I don't know how fast deer can run. Maybe? Probably. They're pretty fast. DRB running at -12 I hat plus 8 J hat, and DRC running at 1.2 I hat minus 18 J hat. What is the velocity of the rock on which they were standing after they all scattered? You don't, no. The gun is not part of this system. Draw what the beginning system looks like. Draw what the final system looks like. And my hint to you all is how many objects are there? And go from there.
Yeah, because like a deer can't just like, I guess we'd have to push off the rock.
Yeah, the rock can have friction. That's fine. The rock has friction, but we don't care about that. It's part of the system, so we're all good. Though, to be fair, they wouldn't be able to run on the ice-covered pond, but that's okay. You know, they jump off the rock, they all hit the ice, and they all start sliding around. They just slide in that direction.
They're all sliding.
Yeah, actually doesn't matter.
What if they jump off?
Doesn't matter. Doesn't matter.
Yeah.
Well, okay, as long as they're heading in these directions, you're fine. That's the cool thing with momentum. As long as you know the initial and the final, you do not care what happens in between. You don't care if one jumps off, then another jumps off, then another jumps off. Doesn't matter.
It doesn't matter the order too, because just like with vector addition, you can start from anywhere.
It's so cool. That's why momentum's so cool. You don't care how they jump off. You don't care what order. You don't care how fast they do. You just care that afterwards they're going as fast. From once their feet leave the thing. The instant their feet leave it, they have this velocity. Draw a picture.
Is it, are these light?
Yeah.
Okay.
Oh yes, they are not plummeting into the earth. Oh, you're talking about gravity.
Yeah. I think I'm
Sure. I was like, I don't give you all enough time, opportunities to chat.
Yeah, I know a friend who's taking 2002. Oh, that's right.
What's this You're on a rock. They're all chilling on them. What is my initial?
You like that? No.
It's just so crazy.
You know how we call them?
Your initial one, your final part, something else about
Romeo and Juliet.
what happens.
Yeah.
This is for drawing it and all that kind of stuff. Try to do it all in your head. You're just super like you're right. Yeah. It's not a good idea. That's the benefit of paper.
You were excited.
Nothing is ever forgotten. Curse as much as a gift. Plummets into the ice, into the surf. No. No, they're not going in. No, they're not. They're not crashing. No, that is not clarified here, but we're going to assume they don't plummet at 30 meters per second, or 30 miles per hour into the rock goes flying up into the air. They're all not moving.
That's awesome. It's truly crazy. And it helps with the math.
All right, if you didn't draw a picture and you're not sure what to do, that's always where you start. Here's a rock. We're going to look at this from above. To clarify here, the J direction is not into the earth. We're not flying upwards or flying downwards. If you just think about it, it's like, okay, yes, Deer C is not plummeting into the ice with a velocity of 30 meters per second downwards. That would be wild. Yeah. We're looking at it from above. You know, here's Deer A. Here's Deer B. Here's Deer C. What color is that one going to be? Green. It doesn't matter where they are. We don't care where they are. That's cool. We just care they're on the rock. All right. Now we got our initial. We now make our final. Oh, and what's special about it kind of looks like a face, which is funny. Do I need to draw any velocity vectors on this? No. What's my initial velocity? 0. Isn't that nice? Everything has an initial velocity of 0. So you can put like initial velocity 0. You can put like A through D or 1 through 4. I don't care how you write this. I just kind of generally do this. If they all share it, I just put it as is. All right, that's my initial. Then my final, this picture is going to get a little bit more complicated. Deer A. So I'll color code these. Deer A is going to run 15 to the right and 5 up. That's going to be something like that. Deer B is going to run negative 12 to the left and 8 up. So that's going to be something like that. We're going to assume they don't hit each other. Fun fact, who cares if they hit each other on the rock? Doesn't matter. As long as when they leave the rock, these are their velocities. And the last one, 1.2 to the right and negative 2. Boom, that's that one. Now, I have no idea which way this rock is going to go. So I'm not going to actually try to... The rock is going to move. I don't actually know which way it's going to draw, so I actually don't want to draw the arrow yet. The rock will move. this problem isn't trivial, and that everything cancels out. I don't know which way it's going to move. We'll have to do the math, but it moves, somewhere. I don't know which way. We got to do the math. Okay. What do we know? And this begins our giant list of variables. V initial A x equals 15. V initial A y equals 5. Green color. V initial B x is negative 12. V initial B y is positive 8. Good times. All right, great. There they all are. The mass of all the deer, mass equals 70. Mass A equals 70. Mass C equals 70. Mass B equals 70. And the mass, we're going to call the rock D. Step 2, what are we solving for? V final. D. I totally do not have enough room. All right, step 3, you build your equations, y'all. In the x direction, sum of momentums initial x equals sum of momentums final x. In the y direction, sum of momentums initial y equals sum of momentums final y. And then we build it. MA plus MB plus MC plus MD. MAV final A. Oh, my bad, y'all. I made a mistake. No one caught this. These aren't initials. Silly me. Those are all finals. I wrote that wrong. Yeah, all the initials are 0. These are all finals, y'all. You can see that in my picture. Oh my goodness. I don't know if I'm going to be able to fit this all in here. We'll find out. M final A. Do I need more than that? Nope, X. Look how thorough I'm being for you all. Facts. This looks worse than it is. It's really not that bad to plug in, y'all. Ugh. I just ran out of space. It looks way worse than it is, y'all. Once you plug in the numbers, this problem's really simple. Plugging in the numbers, it's really not that bad. I'm just writing out every single step so everyone knows what's going on in case you're confused. Great, that's that side. Hey, you know what's cool about the left side? It equals 0. MA, oh goodness. I am not rewriting this whole thing. All right, look, at this point, y'all, you put in the numbers. So step 4, it actually ends up really easy. I'm going to do this one in purple. So purple, so 0 equals, you know what's nice about the deer? They all have a mass of 70. Like 70 times negative 12 plus 70 times plus 200. Look, that's not that bad of a math problem. Okay, look, if that's a bad math problem, your life is going to get much worse. Yes, you plug it in, you divide by 200, and you get an answer. So V final. I don't know what that equals. 15 minus 12. I got 1.47. So the rock's going to move to the right. Negative. Oh, yeah. You got to shift it to the other side. Good catch. It's going to move to the left. Great. To the power of shrinking things. I'm going to make more room. Is it going to move up or down? This is why we need math, y'all. There is no way you can intuitively look at this problem. Like, you'd have to spend a lot of thought looking at this problem and figure you have to do the math to kind of get which way it's going to go. There is some nice symmetry with the deers because they all have 70. You could combine all their vectors and do that and stuff like that. But if these deer had different mass, oh my goodness. Yeah, good luck. If these deer had different mass, you can't intuitively figure out what the rock's going to do. Math exists to let us do complex logic. Just like language exists to let us do complex logic. So now we're going to do the y component. Just putting in the numbers. It is kind of satisfying when you get to the last part, though, and you've organized everything very nicely. Ta-da! All right, y'all. There it is in all its goodness. Yeah, I mean, in this is kind of a, I don't want to say worst case. The elastic collision was a worst case scenario. That was obviously like much worse than this. But this is like as complex as a question on a test could be. Remember a rule of thumb, y'all? I'm never going to give you a problem on a test where most of your time is spent doing math. So remember that. I'm not going to give you all a problem on a test. So remember that elastic problem? Most of our time is spent doing math. I'm not going to give you all a problem where I'm testing you mostly on your math skills. That is important. That is a subset of what I test you all on. But remember, steps 1, 2, and 3 are really what I care about. If it was possible to test you all on steps 1, 2, and 3, okay, I say that. As engineering majors, I do need to make certain you can plug stuff in. Because you have to. If you're all physics majors, I wouldn't use any numbers. But you're engineering majors, so I need to actually prepare you for your future classes. You all actually have to calculate and build real things. Physicists do as well. Physicists make devices and all that kind of jazz. But we like our variables. They're so much easier to work with. All right, great. I'll leave this up for a couple more moments, and then I'm actually going to have Angelina and Leo kind of just chat with you all about universal gravity. We're not going to spend that long. At the latest, we'll go till 10:30 today. And then, as always, if I ever finish class early, and in quotation marks, you can stick around the next 20 minutes, and we'll help you with anything you want. Problem sets, whatever. Basically, just view it as like in-class office hours. But you can at that point also leave, of course. There's not going to be any new stuff. It'll just be if you want help on anything we went through today or anything else, we'll be around. But yeah, I'm going to let them chat to you all about universal gravity because that's the last thing. There's two last things on the upcoming test, universal gravity and center of mass. So the test is going to be energy, momentum, universal gravity and center of mass. Universal gravity and center of mass kind of share space. Great. Yeah. Look at that, y'all. We're on week 9 of content. Isn't that cool? There's actually only 2 more weeks of PowerPoints after this, or 3 if you include this. All right, which one? All right. They have the floor. I may or may not pipe in every now and then, but they like space stuff. This is as spacey as we get in this class, so that's why I'm giving them the space.
Okay, let's start with a super easy question, not a trick one. If I ask you, what direction does gravity point? Shout it out. If I draw this and say this is Earth, what direction does gravity point? Yeah. Fantastic. So when we talk about universal gravity, we're usually talking about some mass, and it doesn't matter if it's big or small, but we'll mostly talk about big masses because that's where gravity really matters. It's important to remember that the gravitational force on that object is always pointing to the center. So we came up with this value earlier in the year called G. What is that for Earth? Yeah, so I heard someone say negative. We're going to overlook that for the moment because, again, it's to the center, right? And when we talked about circular motion, we talked about when things point to the center, that's the positive direction. So if I now draw the moon, what is G equal to on the moon? I'll call this G2. I heard something like 1/6 of that. I actually honestly don't even know if that's exactly the number. But there we go.
Google, yeah, Google knows.
Is it 1.6? Wait, what was it? It was 1.6.
Yeah.
Okay.
Where to go? So the idea is that like the acceleration due to gravity on the moon is less than the acceleration due to gravity on Earth. Leo, why is that?
Because the moon is less massive. Because gravity is proportional to how massive something is. You probably can't tell.
That's, oh my god.
Ooh, that's a good question. Someone asked what about distance?
What about distance? That also plays a relation. And you'll see that. Not today, probably.
Oh, we can still write it
Oh,
out.
yeah, we could write it out.
Okay, actually, oh my god. Do we get to do a clicker question?
Wow, look what a good question.
Do I just hit play?
Yeah.
Okay. Alright, try this out.
That usually means that's a good clicker question if someone asks that question. So. Always makes you feel good.
And it's just like
What is it? Okay.
And you can see there. Oh no!
Did it?
The physical ones. Are the physical ones saying that it's sent or no? No! Alright. No. It's fine. I'm not going to make you pay for something. Alright, remember your answer. We're throwing that one in the trash. There's other people with physical ones. I don't want to penalize you for technical difficulties. It's alright. If you know the answer, you can hit a button again. I don't know what. It maybe got slightly unplugged. You can see the responses
Yeah.
on this, which is really nice.
Okay.
So you can
I
actually see
guess
what they're
yeah.
answering,
That is true.
which I use. That's how I know if their people are doing well or not well.
Yeah.
And if I need to give maybe a hint.
It's glitching again though, the screen.
No! It's fine, it's fine.
Okay.
I'm
As long as it's, yeah, that means something.
It was just like flickering, yeah.
Yeah, we just gotta get to this question.
How many have been responding today?
I just give them look, in a question this simple, you just give a certain amount of time. Like,
Alright, we're gonna go 5 more seconds.
I don't remember. Usually I do that.
Alright. Let's take a look.
Woo!
That is correct.
Yay!
Is
Just
indirectly.
go ahead and poke the right one.
Oh, that. There we
Yeah.
go.
Oh, you can like.
That way
So
it grades it,
okay.
because they technically get a tiny bit of points.
Oh.
So gravity is. What is the word?
Proportional.
But inversely
inversely
proportional to distance. But more specifically, and we'll look at this next class, it's inversely proportional to distance squared. So if you go a little far, gravity decreases a lot more significantly. Yeah. So are we missing something in terms of the concepts?
I don't know. If everyone doesn't know what inversely proportional like really means in your head, you know that the graph for squared, if you just look at the positive side, it goes up by a little bit and it really trails off like immediately. This is basically the inverse of that, which means that the further you go, the quicker it dies off,
Just hit the result.
kind of thing. So it's a good relation to know. I guess that's all I can really say about it.
And then
Let's see what comes up next and see how much you want to get into. All right. Yeah. So I think that's pretty much. Just want to give you all an intro to this. One thing I encourage you all to think about. I'm like. So when we give you all this equation, remember I told you all this class, certain things come from observations of realities, and then other things come from those. The equation we're going to show you all next class for the universal law of gravity, this is from reality. This is a measurement of reality. It is not derived. It is not calculated from anything else. It was done by experiments. And my encouragement to you, my fun thought experiment for you all to think about, how would you determine how force changes with, like, how would you all come up with it? How would you all discover this relationship? If you were doing an experiment, how would you determine this? What equipment would you use? That kind of stuff. And also make certain you place yourself like 300 or 400 years ago. What equipment would you have access to 300 or 400 years ago to come up with this equation? To determine that it's based upon r squared and the mass of an object and all of that. That's the thought experiment because that's what Isaac Newton did. Again, genius. Absolute genius. How would you all determine this given the tools and resources available to you 300 years ago? Let's say you had infinite money. Even 300 years ago. How would you come up with an experiment to determine this? Fun thought experiment. Otherwise, again, if you have problems you want to work on it, this is in class office hours for the next 30 minutes. Stick around if you want, leave if you want. The choice is yours, whatever is the most beneficial to you.
Also, I will say, gravity is a mutual force. So, the force of gravity is determined by two objects acting on each other. Not just one acting. It's a two-way street. You have to have another to have a force.
Sorry.